Friends, today I'm going to show you how to analyze data from the experiment where the design is completely randomized. So let's first know what is a completely randomized design. So it is called completely randomized design when the replications of treatments are allocated at random. So there is no pattern. So if you see the example here, so let's consider this as a field where there are 12 plots. Then there are four treatments: treatment A, treatment B, treatment C, and treatment D. And that means there are 12 units of experiment. And if you see, there is no pattern. So there is no pattern in terms of block, in row or in column. So it's allocated very haphazardly or randomly. So this kind of design is called completely randomized design, which is pretty easy, but sometimes there are a few shortcomings of this design as well. When everything is homogeneous, then this kind of design works pretty well. But if there is a little bit heterogeneity in one block compared to other block, then this kind of design may not work quite well. So on the left side, if you see here, there is no pattern, whereas in the right side, I'll show you there is a little bit pattern. As you can see here, in block 1, block 2, block 3, and block 4, each block has all the treatments in this field, whereas in this field or in this experiment there is no pattern. So if we consider this as one block, this doesn't have treatment C. Whereas if you consider this block, there is no treatment A, and in this block there is no treatment D, and in this block there is no treatment B. But if you see here in block 1, there is treatment A, B, C, D, and in block 2 there is again A, B, C, D, and in block 3 again there is A, B, C, D, and in block 4 again there is A, B, C, D. So there are 4 treatments, and each block has all the treatments allocated randomly. So this kind of design where there is no pattern is called completely randomized, and this kind of design where treatments are randomly allocated in each block is called randomized complete block design. So which design is better? So guys, please have a thought about it. So for example, if there is a if this is a field plot and there is a sunlight more in block 1, then which design would be better? Or if there is everything same in all the block or all the plots or all the fields, then which design is better? So please have a thought. So when we talk about analyzing data obtained from completely randomized design, so this is the table which we are going to use. Either we do analysis manually or using Excel or using SAS. So this is the table that is being used all the time, which is used to calculate F value. So this table is also called ANOVA or analysis ANOVA table, where you use F value to calculate, which is used to calculate F value, which is here. And then if that F value is greater than the F value obtained from F table, which is same universally, then you reject the null hypothesis. But if this F value is less than the tabulated F value, then you fail to reject the null hypothesis. So I'm gonna show you quickly what I mean by this. So let's go to our data. So I'm using this experiment as an example where there are 4 treatments: treatment A, treatment B, treatment C, and treatment D. And as you can see here, there is no pattern. Either if you consider column as a block or row as a block, then there is no pattern. So this is called completely randomized design, and there are 4 number of treatments and there are 24 number of experimental units. So each plot here is an experimental unit: 1, 2, 3, 4 by 6 equals to 24. So let's go to our data, guys, and then I'll show you how to do that using manually, using Excel, and using SAS. So this is our experiment, guys. As you can see here, so there are 4 treatments: A, B, C, and D. And this is the table that I I showed you earlier on, which is used to calculate this f value. And if this f value is um, greater than this tabulated, this is a tabulated f value for this kind of experiment, which you can easily come up in Excel. So for example, if you do a function of statistical, then if you go to this value here, and then probability, usually you say 0.05 or 95% probability, and upper degree of freedom, this is called upper degree of freedom, which is 3 because there are 4 treatments, and denominator degree of freedom will be 20. I'll show you how I come up with that value later on. So if you click OK, then you come up with that value. So this value is basically a f value for 95% confidence level, with numerator degree of freedom 3 and denominator degree of freedom 20. All right, so let's go to this experiment. So there are 4 treatment, 24 plot, and that means 24 experimental units. So basically number of treatment are 4, number of experimental units are 24, and degree of freedom per treatment is 3. So which is basically 4 minus 1. So if you click here, so 4 minus 1, and degree of freedom total is, if you click here, that's 24 minus 1. So we have basically 24 units minus 1, and this is called residual degree of freedom or error degree of freedom. It can also be called error degree of freedom, which is basically 23 minus 3. So 23 is a total degree of freedom and 3 is a treatment degree of freedom, that is 20. So if you see here, so these are our average value that we got from our experiment. So treatment A, we have 6 replicates for treatment A, 6 replicates for treatment B, 6 replicates for treatment C, and 6 replicates for treatment D. And these are the average value for each replicates. These are the average value for each replicate for treatment A, B, C, and D. So this is our data, basically raw data. So this is our treatment total, so which is basically sum of all these here, and then this is again treatment total for treatment B, treatment total for treatment C, treatment total for treatment D. So this I'm calculating this all manually to show you how to fill this table here, guys, because this table, if you know this table, then you will get all the basics of simple data analysis using ANOVA. So this is treatment total, this is treatment mean, so which is basically average of this value here, and same goes for treatment B, same goes for treatment C, and same goes for treatment D. So we are basically trying to see either if there is a treatment difference or not, if there is a difference between treatment A or treatment B or treatment C or treatment D, or if they are same. And this is the experimental total, which is basically sum of everything, which comes to 397.85, and this is a correction factor. So every time when you calculate these things, you have to calculate correction factor, which is basically, if you click here, so H18, so that means sum of total square divided by number of experimental units. And then if you go here, which is a total sum of square, so which is here, so that's what we are going to put in here later on for that table. So this is a total sum of square, which is basically sum of all the squares. So this value, if you see here, are the square of the raw data. So this 201 is a square of individual raw data, and same goes for this, and same goes for that. So to calculate total sum of square, I'm using this square value, and I'm adding that, and then I'm subtracting that value from correction factor, which is this one. So sum of all the squares minus correction factor, and then again I'm calculating treatment sum of square, which is basically square of individual treatment total minus correction factor. So if you see here the formula in this Excel table, then you will get it. And if you want, I can attach this Excel I can give you a link for this Excel sheet which you might use for your own analysis. So so we calculated total sum of square and treatment sum of square. So let's fill this table now, guys. So we know our treatment degree of freedom is which is this basically. So this value, let's put that, and then our residual degree of freedom, we don't know it. So our total degree of freedom is 23, and our residual degree of freedom is this minus that, and every time this is same. And our sum of square, so our treatment sum of square is this value, and our total sum of square is this value, and then our error sum of square is this minus that, and this is our mean sum of square, so which is basically C15 minus treatment sum of square divided by treatment degree of freedom. And this is our error mean sum of square, which is basically error sum of square divided by error degree of freedom. And now finally time to calculate F value, which is already in the formula here. So which is basically treatment mean sum of square, which is D15 divided by error mean sum of square, which comes to 99. So let's just manipulate this table slightly differently. So if if we had 5 treatments, then treatment degree of freedom would be 4, and you can see here the data is changing. So let's not do that now. So let's go to the actual value. So this is our F value, and this is a tabulated F value, guys, for 95% confidence interval with treatment degree of freedom 3 and error degree of freedom 20, so which is here. So that's the value I have come up with from our experiment, which is pretty easy to calculate. So that's the F value, which is the actual F value for that that 95% confidence interval for two-tailed test for treatment degree of freedom 3 and numerator degree of freedom, you can call it, and denominator degree of freedom 20. This is this value. So you can see here, guys, so this value which is our calculated F value is greater than tabulated F value. So calculated F value is greater than tabulated F value, and tabulated F value is same all the time, guys. So let's highlight it. So calculated F value is greater than tabulated F value. So that means so this is the rule I created, guys. So if calculated F value is greater, then I would do 1, and which means reject null hypothesis. So and if calculated F value was less than so let's copy that, Control X. So calculated F value is if calculated F value is greater than tabulated, then 1, if less, then 0. So that is just the formula I created to show you guys. So so now we have got 1, so that means this is greater than that. And let's say if this was 1, then it would be 0. So that means this is this. So that means we accept null hypothesis, but which is not true in our case. So ours is 1, which means we reject null hypothesis, and our null hypothesis is this. So our null hypothesis is all the treatments are same. but we are rejecting that because f value, calculated f value, is greater than tabulated f value. So we are rejecting null hypothesis. That means there is treatment difference, which you can see from even raw data as well. It looks like treatment C has might be slightly different or higher than other treatment, but we are not sure yet. But now we are sure because our calculated f value is greater than tabulated f value. And now let's do the same thing using Excel. So this is our data, which is same as this data. Now let's calculate using Excel. So for that, you need to go to data, and you need to go to data analysis, and then we are doing it using ANOVA, right? So this is called ANOVA, and we only have one factor. What is that factor? That factor is treatment. So we only have one factor. That's why it is a linear model. So let's click OK. And then what is our input range? So let's click here, and then let's just add that value, and we are grouping it by column because column A is treatment A, column B is treatment B, column C is treatment C, and column D is treatment D. And it's not row, so that's wrong. So let's do column. And what is our alpha value? That is 0.05 because of 95% of confidence interval. If it was 99% confidence interval, it would be 0.01, but in our case we are doing 95%. And we can select where we want the final data. So let's click that and let's add it here, and then let's click OK. Yeah, now you got everything. Previously we calculated this manually, guys. Now we got everything, and Excel is calculating everything for us. And this is a single factor, as I already told you. This is a linear model. And let's see if this value is same or different from our manual. So let's copy that here. Yeah, so now you can see, guys, everything looks same. So degree of freedom is 3, residual degree of freedom is 20, mean sum of square for treatment is 74, for error is 0.74, f value is 99.94, which is exactly same. So manually and Excel is calculating the same thing. And p value, so let's make it number, which is less than 0.05. That means treatments are different. Now let's do the same thing using SAS, guys. So for SAS, we need to arrange data like this. So there are total of 24 observations, and these are our treatments, and these are the data for these treatments. So this, as you can see here, so this is our plot, individual plot, where there are 24 plots, and these are the individual data. So this is the table we are going to use for SAS. So let's go to the SAS window, guys. I'm using SAS University Edition, which looks like this. Control V. All right, so this is our data. So now we need to add all the codings. So let's call it data, give any name. So I'll give name CRD because this is obtained from CRD. And then our input is, so the first column is just serial number, and then second column is our treatment, and treatment is in A, B, C, D. So we always have to give a dollar sign. If it is not numerical, we always have to give a dollar sign. And then our dependent variable is in column C, which is let's say it is a weight of the animal. This is just a random experiment, guys. And then let's call it data lines, and then so this is our data. And then let's try to print this, guys, if the data has been printed nicely. So let's run it just to see if the data has been printed nicely. So you will see blue if it is written nicely, guys. So let's run it. Yeah, looks like there is some error, guys. So there should be some data like 1 2 3 4 in serial number, and there should be some data in the weight. So this, there is something wrong in reading of this data. So let's go to the code. So this window is not able to read our data properly. So this is a pretty common thing in window edition. So to fix that, you need to copy this command exactly like this, and then paste in the second row. Enter and Control V. Now if you run this, it will be printed nicely. Let's see. Yeah, you can see here. So there are 24 observations and there are 4 treatments A, B, C, D, and these are the dependent variable. Now let's do actual analysis. So let's go here and then let's click enter. So let's click proc GL because we are using GLM because this is a general linear model. There is only one factor, and we are assuming linearity in there. So then our class is treatment, TREATMENT, treatment. That's the only one factor, and the model is weight equals to treatment, because we are trying to see the effect of treatment on weight. And then let's run it. So this is pretty simple, guys. So general linear model, our class is treatment, which is a independent variable, and then model is dependent variable by two independent variable. And then let's run it. Looks like there is no error. It's running nicely. Yeah, now we can see the data, guys. So let's go down. So this is our data, raw data, and then this is our general linear procedure, general linear model. So there are 4 treatments, number of observation 24, and this is called ANOVA table. So let's see if this is different from our calculated one, which was here. Yeah, and so if you see here, so sum of square is 222, error is 14, f value is 99.94, and same goes with the one which is calculated from Excel, and p value is less than 0.05. That means there is a significant difference between treatments. So if you go further down, so it looks like treatment C is different compared to other treatments. So to know which treatments are different to which, then we have to add one more command, guys. Now from the figure it looks like treatment C is different to other, but what about treatment A, B, and D? Are they different to each other? It's difficult to tell. So let's add one more command after this. So let's get the means of everything. So means of the treatment, then put slash, and then if you put 2 key test, that's what you do to get treatment. So 2 key ALPHA alpha equals to 0.05, which is a 95% confidence interval. So let's run it again. Yeah, let's go down. Yeah, now you can see here, guys. So this is what we got from 2 key test. So it says means covered by the same bar are not significantly different. So if it is covered by same bar, they are not significantly different. So C has different bar compared to all other, so that means C is significantly higher than others, whereas B and A have same bar. So that means B and A are not different. and A and D also have same bar, so A and D are not different, but B and D have different bar. B has green bar whereas D has blue bar, so B and D are different. All right, so thank you very much, guys. Please do not forget to subscribe to our channel and leave your comments or questions if you have any from this video, and I will try to reply to all of your comments and questions as soon as possible. Thank you for watching my video, guys. Bye.